start in with a new mathematical topic called the variational calculus, because Lagrangian mechanics is going to be based on the variational calculus, and all manner of interesting topics, modern physics, are going to grow out of the Lagrangian mechanics. So this topic here is called variational calculus. Write that correctly. And what we start with is a little description of what we're trying to do. And the example, simplest example would be, what's the shortest curve connecting two points in the plane? You guys will say that's a little too simple. Shortest curve connecting two points in the plane, you just know that it's a straight line. Right? So I'll write this down. I'll make it wavy. We can straighten it out. The first one is the question, shortest curve. I'll just say A to B in the plane. That's example one. But what if we were on a sphere? What's the shortest curve connecting two points on the sphere? Same, but on actually I could say cylinder. That would be another question. Or on a sphere. Anybody know the answer to the sphere? Pilots know it. We have to discover it for ourselves. Now you got 2 points on the sphere. What's the shortest curve connecting? And a really famous one, we'll come back to this. This one was easy, right? This one we already knew. A really famous one is the shape of the curve of least time. So I have a curve here, and I slide a frictionless bead down it. And depending on the shape of the curve, things will go faster or slower, right? So this one here is very famous. It's called the Brachistochrone. Curve of shortest time. We have to try to set these up. And then there will be one which is the curve where if you rotate it around an axis, it has the smallest area. So you can see we're trying to minimize something in these problems. Minimize something, well, calculus is something we use for minimizing things. But the answer is not going to be a number. The answer is going to be the function itself. So the answer to this is the function, y equals ax plus b. The answer to this is a great circle. So if you have a plane that goes through the center of the sphere, contains the center of the sphere, then that'll give you the shortest distance from one point to another. So the answer here is the great circle. And this will show the helix. We can show those things nicely. And so that's interesting in and of itself. This is actually before we got to physics, although this one here requires a bit of physics, energy conservation setup. Curve of shortest time, again, this was a little bead that's sliding without friction down here. So that is the variational calculus. That and more, but that's a good set of problems to start off with. So the next thing we have to do is try to get an expression for the length of a curve in the plane. expression for these two here. This one and for this one. This is the one that started the game, started the ball rolling, so to speak. I'd have to look up which famous man it was, but it was the generation of these Isaac Newtons and stuff feeding each other interesting problems to try to solve. And that was an interesting one. Let's see. Okay, we'll set both of these up. I'm going to erase the border. And this one actually establishes a connection to physics, but the connection we're looking for, we will then establish later. Right now we just have some interesting problems. So the next thing, length of a curve in the plane. Length of a curve in the plane, and we'll just get our same old picture going. There's a curve. Down here we have our x-axis, x1 to x2, and we have y of x. So what we do for the length is we just integrate. I think we did this last semester, right? Everybody remember the length element? Root of 1 plus y prime of x squared dx. We did that last semester, right?
Yes.
Yeah. So this is nice. This is a length that we have to plug in some function. And any function, these are well-behaved functions, single values, we're not doing anything fancy here. So if I plug in a function, I get a number. And if I'm really patient, I just plug in every conceivable function. And I've eventually realized that the straight line minimizes this problem. But there's going to be a formalism where we can crank it out and show that. So, we could even do this. We could say L of F equals x1 to x2. This is a little fancier. 1 plus f prime of x squared dx. And then you would say, yeah, I took a function, plugged it in, got the length of the curve. We expect a straight line to minimize this. And as we'll see that it does too. Minimize all of that. But the brachistochrone is more interesting than this, so we're going to set it up as well. So that was one problem. Now this other one, we have to do a little more of an analysis because we're minimizing the time. So again, I'm just going to draw some curve here. We kind of expect it to be this way, right? And shaped like this. What would take longer than this curve?
Straight line.
Straight line. Turns out straight line will take longer. Do we know that by our intuition? Or maybe. What about this one? We could make this one go as slow as we want, right? Because it would just go creeping out here and eventually drop down. So clearly there is, and another one, this one would be kind of ridiculous, but it would also take longer. So you can see that between those extremes, there's got to be one that has the shortest time. That's the kind of intuition we're looking for. But because it's a shortest time, least time, so again, curve of least time. Because it's that, what we're looking for is integral dt equals minimum. So that's what we're going to work with. And because we're physicists, we do this. We say dl equals d dt. And that just flows right out of our hand. And therefore, dt equals dl over d. So we can set an integral up like this, and we already know that dl, 1 plus y prime squared dx, but we need the v. But we said it was a frictionless bead, right? It's going down the frictionless wire. So what we'll do here is we'll say 1/2 m v squared plus 1/2 m v naught squared equals m g y with delta y. Just to remind ourselves what we're trying to do. We're going to release it from rest. Y. Let's do this differently. mv squared plus mgy. That was the, I taught myself a mistake, right? Equals 1/2 m v naught squared plus mgy naught. Okay. So now we're gonna let that one be 0, the initial condition. And of course the m's we can strike all as well. And we just get a very standard result. V equals root 2g y naught minus 1. And that's what we can plug into here. And then we would say, y is a function of x, that's x1 to x2, or x0 to x1, doesn't matter. Or x0, I suppose. What do you guys think? We'll put a box around this one and call it the time.
Question.
Yeah.
Groups have potential, rotational potential on the right hand side to 0, and g why not?
Yes, I can. If I put this to 0, it would just adjust where my origin is. Exactly. And then, but if I do that, then this minus sign implies that I'm always in negative territory. Good, so we have 2, in fact, why don't we just get a box to get the red box. So we now have 2 expressions, and what we see is there are unknown functions in there. So this is a problem for finding formulas and for finding an unknown function. At the moment, we just plug a function in and it gives us the time. We can very patiently go through all the possible functions. We can do a third one, but this one actually has enough. It has enough ingredients here for us to generalize. So as a note here, just to see what we did. Because we're physicists, we remember, yeah, we have energy conservation, that'll get us what we want to know. Same with this thing here, we're physicists, we do the dl dt. That's always a good reminder of how we go about constructing things from the basics. Okay, so the next thing, we have this kind of problem, seems like an interesting problem. In fact, I'm going to break the suspense on this one. We already broke suspense on this one. This one is going to turn out to be the inverted cycloid of all things. A very famous curve that I've already talked about last semester. But now we have to generalize. So I'm just going to point out that this expression expression depends on the derivative of the unknown function. This one depends on both the function and the derivative. The thing that one more generalization of this would be if it depends on the argument itself. And I have one of those too, but I'll put it on my homework. So if we look at the abstract form of this, we're going to be looking for the following. It says generally we are minimizing something of the form phi equals integral some function of y prime, and x dx x1 to x2, where y equals y of x, y prime equals dy dx. That's what we've seen so far. Like I said, I haven't given you an example with an explicit x in there, but we'll come to one of those as well. So this is the general form here. And you know what, I'll even go over here. We'll call this phi of y. Like that square bracket means that you plug an actual function into this thing and it kicks out a number. Function y of x is unknown. So that's our task. Very nice mathematical task here. Once again, the straight line only had this guy. The brachistochrone had y prime and y. And we'll find another one that also has x in it. So this is the general form. So we have to figure out how to tease out that it minimizes, or we'll see later, extremizes. It could also be a maximum by the same argument. Okay, so what to do now? Well, what we do is a construction, and the straight line kind of shows the way, because we already know the answer. So we've got our points A and B, right? Because we know the answer. So any curve that we add to that little straight line, let's say I have a little bit of waviness, that's going to be longer. That's the principle we're going to use to solve this thing. So suppose y of x minimizes phi. Then y tilde equals y plus epsilon times g where epsilon is simply a positive number, g, now we gotta be careful because the label is everything. G of x1, g of x2, 0. So what we're doing here, we're gonna put these tilde operations inside this thing here, and what we're gonna know is, it's not the minimum. Make sense? Stick with a straight line. If I add a little this epsilon is just a tag, a number, just a tag. So let's actually write it this way: y tilde of x, y of x, epsilon g of x. And g is a dash at the endpoint, so it just puts a little bubble in there. And we know that this red line is longer than the one that does the minimization, the straight line. So this is the important key to this whole argument. We're going to do what's called a necessary condition. Suppose y of x is the answer that we're looking for. Then if we add something to it, it's no longer the minimum. So what we do is this, and y tilde prime of x is equal to y prime of x plus epsilon b prime of x. So we'll go with this thing into this expression. So if everything's on the board, I'm going to use this space down here. So now we've got this phi. We're going to look at it as being a function of epsilon, because I'm plugging these guys into here. Phi of epsilon equals integral f of y tilde y tilde prime x dx x1 to x2. Hand this over to you guys, and you'd all be making a real historic mathematical discovery. But I'm going to do it for you. Here's the thing: by construction, this thing with its definitions has a minimum at epsilon equals 0. You guys agree? This thing here, now see, I'm not putting it as a functional of y, but I'm just saying it's a function of epsilon, which is a real number. So this thing has a minimum at epsilon equals 0. In fact, you know what? I shouldn't have even said epsilon greater than 0. I should have just said epsilon is real. That's actually maybe a little better. Yeah, let's stop here for 10 seconds. People see that we've constructed something that has a minimum at epsilon equals 0. The thing is, because of this assumption, by this assumption, it's not, I've said I'm assuming I have that answer, and I've added epsilon times d to it. So when epsilon is 0, I have the answer. It's the minimum. But the thing is, by doing this form, we can use our ordinary calculus. What's the criterion for this function that has a minimum at epsilon equals 0? First derivative should be 0. It's that basic. So because of the limitations of this board, I'm going to put it in right here. So we'll put here by construction. D. Oh, actually, I'm going to complete this thought here for what now feeling has a minimum at epsilon equals 0, and continuing thought up here by construction, d phi d epsilon is equal to 0. And now we're going to run through a really famous stereotypical calculation and come up with something. Okay. And let's see. I'm going to rewrite this. I'll have enough room underneath it to pull it off. chain rule. So we have df dy tilde dy tilde d epsilon plus df dy tilde prime d epsilon. Nothing happens to the dx, to the x, dx. That's just a chain rule. Underneath here, the dy tilde d epsilon is g. So we have df dy tilde g plus df dy tilde prime g prime dx. The second one is going to need an integration by parts. So I'm going to expand this out. I've got df dy tilde g dx plus df dy tilde prime g evaluated at x1 to x2 minus integral d over dx. I need some room here. df dy tilde prime g dx. So the second step was an integration by parts on the second integral there. I've got to erase the crucial elements here. Now I can continue to the right here. So what happens here is by definition G vanishes at the endpoints. Very typical thing in physics. We've got something vanishing at the endpoint, so that's why I can strike this. Then these two have a common G product. So that vanishes at the endpoints. This was integration by parts. So put that in your notes. We have integration by parts, vanishes at the endpoints. And now we have the following. df dx minus d over dx. df. No, not x, y. Sorry. I'll write this down and I will y prime. G dx. Yeah, I'm going to argue the tilde's away right now. Yeah. Now, starting all the way up here, we knew that we had a first derivative that was going to vanish. Okay, so I'm going to put equals 0 here, and I'll say at epsilon equals 0. And that's what kills the tildes. Okay? That's what removes the tildes. So the whole thing, I'm going to stretch it out, the whole thing vanishes at epsilon equals 0. And I no longer have the tildes in there. I could say the same thing on all of these, right? It vanishes when epsilon equals 0. But I won't. Endpoints, integration by parts, will be stereotypical result here. And there's a thing called the fundamental theorem of the variational calculus, where if I multiply this thing in brackets by an arbitrary function, then the thing in brackets itself vanishes. Of course, if this is a known function, you can't say that the bracket vanishes just because the whole thing is 0. But because G is arbitrary, I'm going to do a proof for you. Because G is arbitrary, then the expression in brackets has to vanish. So I'll write it here now. because g of x is arbitrary, the expression in brackets vanishes, and this will give us, I'm going to switch the order here because we're going to use it that way so much. d over dx df dy prime minus df dy is equal to 0. And that's called the Euler-Lagrange equation. Very soon you'll know this better than you know Newton's law because it's that important. You use a lot. So Euler-Lagrange. This is a good derivation, by the way, for you guys to practice and memorize. It's we're going to be seeing a lot of it. So we didn't get the answer we were looking for. We got a differential equation. We still have to solve a differential equation. Nothing comes for free. But yeah, we've got enough time to do our straight line, so we'll tie all everything together. So yeah, but I can see what we did was we constructed something where we could necessarily claim this. It was by construction. We assumed we had a minimum. So this is another condition for that to be true. We still have to solve this differential equation. But this is very useful, and it's going to turn into Newton's law in front of our very eyes later on. So yeah, this is a great chapter. And I think I have this thoroughly enough. If it's all in your notes, you guys can practice it if you want to pursue this a little more. Oh, and by the way, this statement here is called the fundamental lemma of the variational calculus. I'm going to prove it, but I want to do our example first, so the timing's just right together. So this is the fundamental lemma of the variational calculus. It's really something similar to what you're going to see a lot of. Who's that 107 yet? Anybody? Have you ever heard of going from the differential to the integral form of Maxwell's equations? That kind of thing. Super. Fundamental lemma of the variational calculus. Okay, so what I'm going to do is apply this to the straight line problem and prove that a straight line really is the shortest distance between 2 points in a curve. So I'm going to erase this. This is our grand result here. We'll call this example straight line. Line in a plane. We had a function f for the straight line in the plane. Anybody look at their notes and see what it was? Which one was it for a straight line? Or for a line in the plane? Curve, length of a curve in the plane. Not the integral, just the function inside the integral. Plus,
in brackets, y prime of x squared.
here we go, y prime of x squared. So this is the function, so f generally is f of y prime of x. Here it's only literally a function of y prime. Okay? So this is the one we're going to take into this differential equation, and it's an easy one. Straight line turned out to be a hard one, would have been some kind of problem. So what we're doing is we're taking this f and applying this operation to it. And for one thing, what you see is the partial f with respect to y is 0, because there's no explicit y in here. be a constant. Because you see we have d over dx of this thing is equal to 0. Right? So this itself must be a constant. That's why it's going to go fast. Or 1/2 root 1 plus y prime squared 2y prime equals c. Cancel the 2's. So you can say this is our differential equation to solve. And it's trivial. But we'll go through it anyway. So yeah, I just did this operation on that thing here in a little more order. Here we can just declare victory. Let's go ahead and have a look at it. So we have y prime squared equals c squared plus c squared y prime squared. If we multiply it out, y prime squared equals c squared over 1 minus c squared equals a squared. Just for the sake of argument. And then y prime equals a equals constant, therefore y equals ax plus b. And that's the equation of the straight line. So that would be all the steps. That's really, this simplest example is also the one to really understand it by. At this stage of the game, we have to solve the differential equation. Could get very complicated and difficult. Straight line wasn't. Good. That's all we're going to do for today. I'm going to owe you this fundamental lemma. That's a fun one to discuss as well. And then what we'll do is some applications. It's a little bit early for me to assign something. It is. That's just the way it goes. Friday we'll get some assignments going. If you want to play around with that derivation, now you'll see. A lot of fun. Okay, good.